Okay, let's move on to part 3 of our discussion of the H2 plus molecule ion. In the previous videos, we talked about how there are two MOLCAO type wave functions, molecular orbital as a linear combination of atomic orbital wave functions. They're psi plus and psi minus. And we went about normalizing these wave functions. We came up with this normalization constant out front. That is this 1 over square root of 2 times 1 plus s. That's times psi 1sa plus psi 1sb. And those psi 1sa and psi 1sb are the hydrogen 1s atomic orbitals, each centered at their respective nucleus for this H2 plus molecule ion. Similarly, we get this psi minus here, and working through the integrals and normalizing, we get this 1 over square root of 2 times 1 minus s times psi 1sa minus psi 1sb. And we had a few things left over to sort of wrap up what these wave functions look like. One is we need to evaluate this overlap integral s. And you recall when we try to normalize, we end up with these integrals that look a little bit like this one here, where we have psi 1sa star psi 1sb d tau, the integral of that overall space. And let's look at this integral graphically. This is sort of an approximate graph here, where I've taken a slice along the internuclear axis of what these wave functions look like. And I have psi 1sa here, and I have psi 1sb there, and they're going to be peaked at their respective nuclei. And we look that in between those two wave functions, there's this region where there's some overlap, and I've shaded that here. And that overlap essentially represents more or less qualitatively, a graphical representation of what this overlap integral looks like. So these wave functions are not orthogonal to one another. So when we integrate over both of them here, we're going to get an expression that's not zero. And we don't need to work through the details of the integral, but we can look at the result here. The result is this integral, is this expression right here. S equals e to the minus r times 1 plus r cubed over 3. So it's this essentially exponentially decaying function. And also I should point out that r here is in atomic units. And when I look at a complicated function like this, I like to look at some simple cases or some limiting cases to give an idea of how to sketch this function, what it looks like as a function of r, where here is the internuclear distance, capital R. So at r equals 0, we plug that value in, we get e to the minus 0, which is 1, and then the part in parentheses, we get 1 plus 0 over 3, and so the end result is that s equals 1 at r equals 0. Similarly, we can plug in r equals infinity, and we see that s equals 0. So the overlap is 0 at r equals infinity. And at r equals 1, it's somewhere in between. Let's see, if we plug in e to the minus r, that's e to the minus 1, that would be 1 over e. And then 1 plus r cubed over 3 would be 2.33. So we get a number that's 2.33 over e. E is 2.78 something. So we get a number that's less than 1. And so this is starting to give us a picture for what this overlap integral looks like. And it should look roughly like this graph here. where we have s as a function of r, and we have this exponential, more or less exponential decay. Of course, it's not going to look exactly exponential. There are these other sort of polynomial in r terms, but that gives us some idea of how this varies as a function of r, and it's good to have that in mind as we move on to the next steps. So now that we've defined s and we have a properly normalized wave function, we can actually sketch maybe what these combined wave functions look like. So here I've, again, as above, I've sketched the two individual atomic wave functions, psi1sa here and psi1sb there. And if we add them up, we end up with this more or less dashed line here, where we've got extra electron density or extra wave function amplitude in between the two nuclei. And because it's normalized, that ends up actually shrinking the amplitude of the wave function on either side on the outside of the two nuclei there. And this is starting to look like a wave function that is corresponding to some kind of electron sharing phenomena where the electron is shared between the two nuclei. It spends a fair amount of time in this region between the two nuclei where it can experience the attractive potential of both nuclei. Also, it will be partially screening each nucleus from the other nucleus by sort of effectively canceling the charge. And so this, we expect this to be a bonding orbital. Now let's look at the psi minus case. On the one hand, we have psi1sa here. I've shown it as positive. I have psi1sb. That's our negative going wave function there. And then if we add those two together, of course, there's going to be cancellation. That's going to be a perfect cancellation in the middle, right between the two nuclei, where we're going to have a nodal plane. And so for nucleus, around nucleus A, we have this positive wave function, then it goes to 0, right in between the two nuclei. So we have a nodal plane, and then it goes negative. And this, as we'll see, corresponds to an antibonding orbital because it ends up pushing more electron density on either side of the two nuclei. And you end up, because there's a nodal plane in between the two nuclei at the halfway point between at sort of r over 2, this has the effect of essentially reducing the amount of electron density in between the two nuclei. And so the electron is not experiencing this most attractive part of the Coulomb well presented by the two nuclei. And it's also not doing as good a job of screening the nuclei from each other. And this, as it turns out, will be an antibonding orbital. Now I'm going to introduce some different nomenclature as we progress here. There's this notion of having a Gerada or wave function with an even inversion symmetry, or ungerada, a wave function with odd inversion symmetry. So these are labels that we attach to wave functions that are a shorthand that help to remind us what the overall shape of the wave function is. And the basic scheme for deciding whether or not a wave function is Gerada or ungerada is we place the origin at the center of the molecule. We replace, so there, we replace x with minus x, y with minus y, and z with minus z. And then we look at the wave function. Does the sign of the wave function change? If not, then we say it's an even or Gerada wave function. If the sign of the wave function does change when you do that, then we say it has odd inversion symmetry and we label it as ungerada. And so now we're going to switch to this other notation where psi plus is replaced with psi g, and psi minus is replaced with psi u. Okay, now that we have tackled the wave functions, now we can move on to the problem of calculating the energy of this molecule ion. As you may recall, we're using a variational approach where we have a parameterized wave function. And here our parameter is r. It's this internuclear distance between the two nuclei. And our variational energy here is given by the expectation value of the Hamiltonian for psi g. And to evaluate that, we calculate this integral, psi g star h psi g. And it's worth noting here, just because there's a lot of things going on, it's good to pause and consider what's going on here. Here we're calculating the expectation value for a Hamiltonian. It's the true complete Hamiltonian. It's not an approximate Hamiltonian. However, our wave function is approximate, and therefore it's not going to be a true eigenfunction of this Hamiltonian, and therefore we're calculating this expectation value of energy, or expectation value of the Hamiltonian, and that gives us our variational energy. We're going to integrate over the coordinates of the electron, but we'll end up with a function that is a function of r, say Eg of r, big R, where r is the internuclear distance. Then following the variational approach, we're going to set dEg dr equal to 0, solve for r. That's going to give us our equilibrium internuclear distance, r sub e. Not only is that a parameter of our model that gives us something to minimize, that allows us to estimate the energy of the system, it also gives us the bond length according to this model. Then once we've determined the bond length, we plug that bond length back into our energy expression, e.g. as a function of Re, and that's going to give us the energy of the molecule. We can even go a bit further and estimate a bond energy. A bond energy would be equivalent to the energy required to move the internuclear distance r from initially a value where it's at the equilibrium internuclear distance, and then we are pulling the molecule apart. So we're calculating how much energy is required to move to set r equals to infinity for the system. And so the energy difference, final state minus initial state, would be E r equals infinity minus E at r sub E, at our equilibrium internuclear distance. And so once we calculate that, we'll know what our bond energy is, right? How much energy is required to pull apart this molecule. And if we think about it for a minute, what is the energy of an electron in the orbit of a nucleus? And then there's another nucleus, but it's off at infinity. Well, that's just going to be E1s for the hydrogen atom. That's just going to be, we're just going to end up with a hydrogen atom with another nucleus that's so far away it doesn't matter. And so the energy of that system is going to be the hydrogen atom 1s energy. Now, before we turn the crank and put these wave functions in integrals and break this up into various terms that we're going to evaluate, let's consider what we expect E of r to look like. Right? It's good to have some idea where we're going, where we're headed, um, in case as a guide to make sure that we're not forgetting something. And so I like to consider some physical arguments for what E of R will look like. And we'll discuss that in the next video segment.